Okay, good morning everyone. Can you hear me? Okay, perfect. And can you see my screen? Perfect. So today we are going to talk about a specific kind of equation, right? We are going to talk about conservation laws, uh, which are some equations that you have already been kind of solving, right? When you were solving the wave equation, advection, you were solving essentially a conservation law, and we will talk about it, about what it is, and also we will explain a bit, for example, what's going on with the Barger's equation that we mentioned previously, right? So the idea of conservation laws is that sometimes physics and in other areas you have some quantity that is conserved during the evolution, right? That quantity can be many things. Could be the energy, it could be the mass, it could be maybe you are talking about cars in a highway and you think, okay, the total amount of cars that I have in the highway will remain constant during the evolution, right? So these kind of equations try to preserve that, try to tell you, okay, there is some quantity that's going to evolve time, and the total quantity will be conserved. So in this equation, right here, we can think as if we had some scalar field, right? Some u that will be some density, some energy density, some mass density. Maybe it's a traffic density that tells you how many cars are in a for kilometer a highway, right? And we will also define some flux, which will represent this function f, the function, the flux of the scalar field. And in this case, we can express the evolution of the conserved quantity inside any given volume, right, by this equation. Right here, we are talking in one dimension. So if we integrate this density u in A and B, right, this will give us the total amount inside the volume. And the rate of change of the total amount inside that volume will be equal to some flux in the extremes. Okay, so I want you to visualize this. What this is telling us is, imagine that we have some highway and some cars that are going through the highway, right? And I take, for example, how many cars are there between the first kilometer and the second kilometer, right? Okay, the amount of cars that I have in that volume, right? How much it changes will only depends on how many cars are entering and exiting at the extremes. There are no other ways in this case for us to get more or less cars inside the volume. If no cars are entering or exiting, then the rate of change of the amount of cars will be zero. Other way, the rate of change will be the flux that we have at the boundaries. And this equation here will need to hold for any volume that we choose. Any interval that we choose, A and B, we need this kind of equation to hold. Of course, we could always take A and B to go to infinity, right? And in that case, we will have the fluxes at infinity. So if we assume that at infinity the solution goes to zero, it tells us that the solution, the total quantity, will be conserved, right? So for example, if you are talking about maybe U is the density of mass, if you assume that the density goes to zero at infinity, then the total mass of the system will be constant. Or maybe the energy is the one that goes to zero, or the momentum, right, or the amount of cars, whatever it is that you are trying to evolve, right? So this equation, very, very powerful. But when we see it like this, maybe we do not yet see some differential equation, but we can take a limit, right, and try to make a and b very, very small, and this will transform into a derivative, right? So because this volume is arbitrary space, by the fundamental theorem of calculus, right? When this omega is infinitesimally small, we will get this equation, this pointwise equation. Okay, so if you see these two equations, essentially this one integrated will give you, integrated in space will give you this equation right here. Here we integrate in space. Here we also integrate in space because this is a spatial derivative of the flux. We will get the flux at the, and this equation here is a scalar hyperbolic conservation law. And we will see that the information that we have of the solution will propagate here with some finite speed across the. Of course, we could also add some source terms, right? So maybe we were talking about the highway, and there are cars that are entering because they are going out of their homes and entering the highway from some other way. That we can enter here as a new term, right? As a new source term directly. That depends on the position. Maybe we are seeing a flux of air or some gas, and we are adding some gas. So the conservation law will change a bit, right? So the evolution of the equation will change a bit, but essentially the idea of what's going on will not change that much. So you will not have that problem. It's just adding some point or some region where you are adding more matter to the system, right? But how the equation behaves in general will not change. Okay, we will still have characteristics and stuff like that that we will see later on. The idea of this part is to understand the problems of of this kind of formulation, right? Because we will see that this kind of solution, this kind of equation, even though they look very simple, very harmless, they will form shocks. They will form discontinuities generally, right? If you take some f that's convex, u, then we will form a shock. And when you solve this numerically, you will see that here we need to be very careful about how we treat the derivative and how we do stuff space. But regarding the source term, essentially the only thing that we need to do is just to plug it in. Say, okay, here maybe I am entering some water, maybe here some cars are entering, or stuff like that. Okay, maybe this is a kind of dissipation, whatever it is. So let's go to our example, right, with cars, right? So imagine that we have some car density, rho, and our u in this case will be rho, right? No, the variable that we are trying to evolve is not the amount of cars, but the density of cars. And so we have also some traffic flux, right? So which will tell us how many cars are entering or exiting a given domain, right? Which will essentially be the speed of the cars multiplied by the density of the cars. That will be the flux from the boundaries, right? So the problem here is to determine what is the speed of a car. Okay, so maybe we have this equation here. This is a very simple idea where we have the speed of a car, will be 1 minus some maximum velocity, which will be the velocity that a car reaches when there are no cars on the highway, times 1 minus the density of cars over some maximum density where all cars are one next to the other, right? So we cannot have infinite density, we must have some maximum density here, and we assume that if all cars are one next to the other, then the speed of the cars will be 0, right? They will be stuck there. Okay. In this case, the flux here will be, like we said, the density of cars times the velocity, and this will be our F. So this is a plot, right? So this is the flux rate versus the density of cars. This is the variable that we are trying to evolve. This is the many values it can take. It can go from 0 to 1. This is the flow rate that we... And this is now our conservation law in this case, right? This is of the form the derivative, the time derivative of rho plus some flux derivative, the special derivative of the flux equals 0. This is the flux. This is the special derivative of the flux. This is our solution. So we are trying to see how we can solve this, and we will first try to solve this numerically, analytically in some way. So we will do something that is called the method of characteristics, right? So we will draw what are called characteristics lines. So let's imagine that we are in the space and time diagram, right? And we have our initial solution at t equals 0, right? Some distribution of cars that, and we want to move in a curve around the x and t coordinates, right? So we move some curve, and we want to see in that curve what is the value of the car density or whatever quantity that we are trying to, right? So we have some path here, x over t, that we do not know yet what it is. And in particular, we want to see through what path the solution is constant, right? So maybe we gave some initial data, and we take some point, for example, and there the car density is, I don't know, 0.3. So I want to find a curve in x and time where the solution is still 0.3, right? When we move, this is continuous in that trajectory. Okay. So in that case, we want essentially this, the time derivative of the conserved quantity u evaluated at x dt t must be equal to 0. So up to this point, are you kind of following me what we're trying to do here? Please write it in the chat if you don't understand what I'm trying to do here. But when we take this equation here and we evolve, time derivative will transform into a partial derivative of with respect to time, plus some spatial derivative, right, of the first component, times the derivative of x over time, right, the speed, the rate of change of the curve that we are trying to follow. And in this point here, we can apply the partial differential equation that we have, right? So we know that u t plus f ux equals 0, right? So here we have ux, and the ut here we can change by the derivative of f with respect to u, to x, right? And this one here we can also change, substitute by the derivative of f with respect to u, right? So in this case here, we have f prime is the derivative of f with respect to u times the derivative of u with respect to x. And when we go one step further, we have this, right? We have that the spatial derivative of u, right? will be times the derivative of x over time minus the derivative of f over u. This, right, will be the rate of change of u when we move across some arbitrary curve x. So what we would like to have is for this rate of change to be 0. So we are moving in some curve where u does not change. So if you want that to be true, and assuming that the derivative of u is not 0, then this term here must be 0. And if this must be 0, that means that the tangent of x must be the derivative of f with respect to u. Okay. So I think, okay, I am here, I have the solution, I am at a certain point, I calculate the derivative of f, I put it at that point, and that will give me the tangent of the curve that I am trying to follow. But notice that we are inside a curve where u is constant. So this value here along the whole curve will be constant. So this here is giving me the equation of a straight line. Because this value here, tangent of the x curve, will be constant during the whole evolution, the characteristic line. So this tells us that there is a characteristic line, right, x over t, which will be equal to x at the initial time, right, plus the derivative of f times the time. So is this part kind of clear? Are you following me here what we are trying to do? Okay. So we do some quick check and we go back to the advection equation that we had before. So in the advection equation that you were seeing before, where we have the time derivative of u plus some speed times the spatial derivative of u equals 0. This is exactly the same as taking the f flux to be some speed times u, right? So in this case, f prime will be c. C. So the characteristics are these straight lines are parallel with tangent c. So this is the solution, right? So imagine that we have some initial condition that is a bump, and we try to move it. In the advection equation, the solution at time t equals the solution at the initial data at x minus c times t, right? So the whole information of the system is propagating one side, right, at constant speed. And this is what we are seeing in this plot here, right? So we have some x time, and these are all the characteristic curves, right? So we have some initial data, and the data that we have will propagate along these lines. So if I have here the solution 0.3, okay, I follow the line, and then I will have 0.3 here, 0.3 here, and 0.3 here, and we will move all together. So this is telling me that essentially, if I have the initial data and I have the characteristic lines, I can have the solution for any time I want, because I just plot my initial data, I plot some lines, and I just follow it and say, okay, along this line the solution is constant, and I have no issue. Moreover, if you notice here, when we are moving around the characteristics, this is for to see, here I am saying the solution has to be constant along the characteristics, and I am not really using here that I could imagine that this data that I am giving could be as sharp as possible, right? So this is kind of a spoiler of what's going to come later on. But we could imagine the initial data, instead of being very smooth, to be some discontinuity, right? And then we would expect, okay, this continuous function, maybe I cannot derivate it, right? Maybe I cannot actually solve it using this formulation because I do not have a well-defined spatial derivative because I have some discontinuity. But I would expect that solution, that initial data, to move along the characteristic lines some way or the other. So now we go to our bump equation and try to draw the characteristics, and suddenly we start to see that we run into some trouble. So this is the initial data, and remember that the tangent of the characteristics go with f prime, the derivative of f with respect to u. And f is here, this is f, right? This is parabola. So the derivative of f will be some straight line, which means that the slope of the characteristic will be proportional to the data, right? So see here, right? If we are with a zero solution, right? The solution is zero, then the propagation lines are straight lines, right? This is kind of like advection. But as the solution is bigger and bigger, the slope is larger and larger, okay? The value of the slope has to do with the initial data. So we propagate this over time, and what we start to see here is that here the lines are kind of going apart from each other, but in this region here in particular, all the lines go together. They merge at a single point, right? And they continue to cross for a whole domain. And if we try to follow the characteristics, right, and I say, okay, I have this solution at this point, or at this point here, and I follow, right, we will see that the solution will start to deform up until some point where there is a strong discontinuity, there is a shock, and later on, this evolves into some kind of weird way, some multi-valued function, right? So that each point here, we have several possible values for the solution, which clearly does not make much sense, right? Because we are talking here about car density. Maybe there are some problems where this does make sense, because as you can see, this kind of looks like a wave in the ocean, like this breaking, right? So maybe if you are doing some shallow water equations and you're trying to model the height of the water, right? The height of the water will have this property where suddenly you have a shock and you have a wave that's forming, and then the wave breaks. So for some small time, maybe this is how your solution will look like. But in general, that's not the case. This could be car density, this will be an energy density, this will be a matter density, this will be momentum. Whatever it is, we cannot allow our solution to be multi-valued. And let's try to maybe understand what's going on here. What's the interpretation of these characteristic lines in this case, right? So we had this initial data here. So here there are almost no cars, then there are more cars, and then there are almost no cars again, right? So where there are no cars, cars are going at the maximum possible speed that they can possibly have, right? They go at, I don't know, 130 kilometers per hour, and they go at that speed. But when they are merged, when they are all together, right, the speed of the cars will be slower. So these cars here are moving slowly, 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 and then they go back fast. So this part here, where we have slow cars and then fast cars, has no issues, right? The fast cars are going at their given speed, and they are going away, and they will never see the slow cars that are behind them because they will never catch up. But in this part here, what we have is some cars that are going the maximum speed possible, right? And they start to bump into the cars that are in front of them, that are going slower because they also have cars in front of them that are going slower still. So this will give us some shock formation, right? And this shock formation will actually be, in this case, a traffic jam, right? So suddenly you have cars that are stopped, and that wave is propagating across the distribution of cars, right? And so this is what you will see in a highway. So when you are suddenly driving and you notice that all cars are stopping, okay, this is what's happening. This is what's happening. Some cars are trying to go fast and they are running into cars that are going slowly because they have cars in front of them and a higher density of cars in front of them. This clock here will form at a finite time. This will always form at some finite time in the future. What you will later have to do is to prove as an exercise here that for the Barker's equation, which is very similar to the one that we have here, where we have the time derivative of u equals 1/2 of the spatial derivative of u squared, right? The time information will be minus 1 over the minimum of the spatial derivative of u. And in general, the shock formation, I didn't put it here, but I will put it later on, has to do with the second derivative of the flux function that we have here, right? In advection, we will never have a shock formation time because the second derivative will be 0, so this time will be infinite. But in Burgers, for example, the second derivative will be 1, so this is what's in here, and in other part, it will always be also be something that has to do with the derivative of u with respect to. But this shock will form at some finite time. So maybe for some time we can assume the solution is smooth, but eventually we will form some. So how do we solve this equation? How do we approach a solution that actually makes sense? Because as we can see, the equation that we have has a spatial derivative. So everything we've done up until this point using the characteristic lines kind of breaks down after this point. Because after this point, the spatial derivative is not well defined. The spatial derivative of the flux of u is not defined. So we cannot just continue crossing characteristics and hope for the best. We see that this gives us a multivariate solution. So we need to take a different approach. And the first approach that we will see is what's called the vanishing viscosity. So imagine that we have again the advection equation, right? And the advection equation maybe is describing some, imagine that you have a river that is flowing at some constant speed, and I put some drop of ink in the river, and that will give me a distribution of ink in a certain region, and that will move with a constant speed along with the stream of the. This may make sense for small times, but eventually we expect there to be some turbulence or some diffusion of the ink, and for that stain that we made to kind of fall apart and try to mix with the water. Right? So in that sense, the advection equation is good for small times, but eventually it does not have much physical sense. So we would like to add some term that is telling us, okay, this shape is actually diffusing. And what we expect is that for that change, right, of that diffusion to be proportional to the gradient of u. Right? So the more u is changing in a certain region, the more diffusion we will have. And the more constant it is, the less diffusion we will have. We will not have much mixing there. Right? So in that case, we add some diffusion flux here, which will be minus some value d, some constant d greater than 0 that we want to add, times the gradient of u, the derivative of u in this case. So now our flux will not only depend on u, but also on the spatial derivative of u. and this will be the new dissipative advection, the advection diffusion equation, right? So this will be our new flux, and this will be our new equation. Here I will fix or here. Now, this problem, we have a second derivative of u in the evolution. Someone has their microphone. I don't know if there. So this equation here is very similar to the one that we had before, but it's now no longer hyperbolic, but it's now parabolic, right? So this equation here will have a smooth solution, as we have seen. Even if the initial data is discontinued, this will evolve into some smooth solution over time. So if we have some shock, right, some discontinuity, what this will do is try to smoothen it out. I tried to make some plots, but I failed at doing them, so I will try to show you here in this book. So imagine here, so right. Imagine that we had the Berger's equation, right? Or this equation will present some shocks, right? The same way as the traffic equation, and the evolution will look something like this, right? So here the the flux is u squared, right? This will also present some shocks, but we can add some small dissipation term here, some minus epsilon times the second derivative, and this will make the characteristic line crossing to disappear, right? And we will always have a smooth solution. So imagine that we are having a very small epsilon and we are in a very smooth part of the solution. The second derivative of u will be smaller, right? It will be closer to zero, so we will be dominated by this term here. We will be dominated by the Berger's equation, and we can expect something to be like these characteristic lines that are moving. But as we are closer and closer and closer to this continuity, the second derivative term will dominate the equation and will start to try to smoothen it out, right? It tries to average the solution across that region with respect to this parameter here, epsilon. So if we do this, we see that when we change epsilon, right, we had our wave here, instead of going abruptly, which is the dashed lines, right, which is the discontinuous shock solution, it will begin to smooth. And the smaller the parameter epsilon I am putting there, right, the smaller the viscosity is, the sharper the solution will be. And this kind of makes sense, right? So we expect there in physics, in problems, to be some kind of dissipation, and for this to be the limit where we actually do not have any dissipation in our system, right? So imagine that we are seeing a gas and we have some shock wave. Okay, we expect that maybe if you look from afar, the function is discontinuous, but if you look very, very, very closely, you will see that it's not actually discontinuous, but it kind of smoothing out. So what we expect as a solution in this case, and this is a very strong solution, is for the solution to the Vargas equation or for any hyperbolic conservation law to be the limit when epsilon goes to zero of the dissipative formulation of. So we add some dissipation term by epsilon to make the equation parabolic, and we get some series of solutions, and then we go to the case where epsilon goes to 0, right? And then we will get some discontinuity, and we work with that problem. You can always make that when you have this kind of problem. You can always add some dissipation. We will later see that tomorrow, maybe, when we talk more about the numerical schemes that solve this kind of equation, that essentially what ends up happening is that there is some dissipation term, right? That smoothing out the derivative close there, but tries to keep it as sharp as possible. We want to keep the discontinuity as visible as possible. This problem here, as I add here as a note, you can make some variable change here, change the u by some p that has some logarithm. I didn't put it here, but you can essentially transform the system here to some heat equation and solve from there, right? So this is solvable, and from there you can get the Berger solution. So up to this point is the problem clear, right? So I want you to understand why these characteristics are crossing, and that there is a shock that will form, and that the strong formulation that we had of the problem here is not holding. So now I want to point out that when we started the class, we started with this formulation here. We started with some integral over space of u equals the flux at the extremes of some domain. So when we see this equation here, we notice that at no point here am I taking a spatial derivative. The u function that I am using here is just some u function. And here I did something very tricky and assumed that u was smooth and differentiable to make this, to go to this step here, right? To transform this into a spatial derivative, right? So here I made some assumption on how the solution is, behaving. And this is why the strong formulation maybe breaks down, right? Because we were actually trying to solve this problem, and we made some new formulation of the problem, which is valid as long as the solution is smooth. But that is not generally the case. So we will try to take the strong solution and go back to the weak solution that we had at the beginning, right? This here. And for this, we will talk about a bit about distributions. So in this case, have some u, and let us consider the space of test functions p that are continuously differentiable in the whole interval in space, right? But which are of compact support, right? That means that phi is some equation, right? Some equation that we have that is once differentiable. So it has one defined derivative, but maybe not two. At least it has one derivative that is defined, right? And it has compact support. That means that eventually it goes to 0, identical, right? So if we go to infinity, the solution will go to 0. And we multiply our equation here, or scalar conservation law, by this test function. Yeah, it works with piecewise differentiable functions. Yeah, I think that's right. But in this case here, what we are doing is multiplying our equation by phi and integrating both in time from 0 to infinity and in space from minus infinity to infinity. And we expect this to be 0. So here we can integrate this equation by parts. And when we do so, we get this new equation here. We integrate by parts here, and we take the derivatives, right? And we have now that the time derivative of, we have here an integral of the time derivative of u. Sorry, we have an integral of the time derivative of phi times u plus the spatial derivative of phi times times the flux integrated in the whole domain must be equal to this equation right here, where we have essentially used the fact that the phi is 0 at the extremes to cancel out some of the terms, right? Some of the terms of the equation, when you go here to here doing the integration by parts, you will have to evaluate phi times u plus f at the extremes, and that part you can just throw to 0 because phi goes to 0 at infinity, right? It has compact support. So notice here that this formulation here, we started with some equation here in the strong force, but now we wrote it in some weak form, where essentially we have some u that we are trying to solve, and we will say that function u is a weak solution of our differential equation, right, of this strong differential equation, if this equation here holds for all possible p's of compact support and that are continuously differentiable. So now we are not asking u to be differentiable, but for this equation to hold for any possible phi function that we want to use. So if we do this, we can actually see that the solution that we get will also be the solution of this integral here that we have here. That may not look as such at first glance until you notice that this phi, I can make it however I want. So I can essentially make it 0 everywhere, and then at some interval a here that I want, it smoothly goes to 1, and then it smoothly goes to 0 again, right? And I take those limits, and this integral here will essentially transform into this integral here when I choose that specific phi. And because I can choose any phi that I want, I can choose any of the intervals I want, so I get back this equation here. So by choosing the test function as I want, I can essentially recover the equation I had at the beginning, where here I am also integrating in time. So this is what you are seeing. Okay. Okay. So now we will give some solutions to this equation. And the only thing that we will be asking the solution is to obey the weak formulation equation. We do not care that much now about the spatial derivative. We integrate over it, and we do not see it. We do not see the shock, essentially, when we try to solve the problem. This insight is very useful later on when we try to solve our equations numerically. This equation here will be our best friend, because up until now we were seeing that maybe you are solving Law 3, there is an exercise which tells you, okay, try to solve the Burgers equation using your finite difference schemes, and it immediately breaks down, and this is why, right? Because essentially you are trying to solve, you form a shock, and you are trying to make a numerical derivative at a point where there is no defined derivative. And also you will try to move essentially the Fourier modes of the solution at different speeds, but close to the discontinuity you will have a lot of Fourier modes, right? A lot of sines and cosines with very high frequency that will start to mess up your equation. So when we see schemes that try to solve this equation, they will try to work with this equation. And in general, what we'll try to do is not essentially to solve for u, right? So remember that we will have our spatial discretization at some points 0, delta x, 2 delta x, 3 delta x, and so on. So now we'll not be solving so much the value of u at a specific point, but the average of u over a certain domain. So the average of u in the space between delta x and 2 delta x, between some point I and y plus 1. So here, this integral here, instead of being from a to b, will be, for example, between 0 and delta x, or 3 delta x and 4 delta x. So now we will be evolving the average of u, which is very close to u, right? It's now an average, and we will use methods that take this into account to solve the equation, right? And we will not as much have to. We will get something that is very close to a derivative, but we will have some dissipation term, and the method itself will be focused on conserving the quantity more than anything, right? Knowing, okay, this is a conservation law, there is a quantity that must be conserved. I don't care as much about discontinuity. I care about the quantity being conserved. Time, okay? So I wanted to ask you if there are any questions up until this time. Is there something that you want to revise? Okay. So I will assume that up until this point, we understand that there are characteristics that they are fixing, and that we cannot continue with the strong formulation after the shock forms, and that there are two approaches. One is to add some viscosity and give the viscosity to 0. Another is to consider weak solutions of the equation. So to better study what's going on with the shock, we will talk about the Riemann problem. So I will introduce the Riemann problem, try to solve it a bit for shock that is propagating, and then we can go to some break and continue after I finish this. So to analyze how a shock wave is moving through space, maybe the best idea is to simply imagine that we have some shock. We construct a shock that we want to propagate, and we go from there. So we will essentially use this solution here. So we will give some initial data where we have some value of u on the left that is constant, and then there is a discontinuity, and the solution is now some other value r, right? And you can later imagine that at infinity, maybe that u goes to 0 if you want to be certain about what's going on with the integral, but we are close to a region where this is valid, right? And we will not have much problems with this, because we can always think that the part where the solution goes to 0 is far apart, so we are not seeing the characteristics of that part of the equation. They are not colliding with the domain where we are seeing the solution, right? So we have maybe this goes to 0, and there is no issue with it, right? And we are trying again to solve here the Vargo's equation in particular, but the results that we get for the Vargo's equation will be very easy to translate to results for a given any flux that we want. So in this case, we want to integrate, right, from minus a to a, the u here up, right? We are taking this equation here, and this will be equal to the flux at the extremes of some domain that we have. So we are integrating from minus a to a, the conserved quantity u that we want. And this will be equal to 1/2 times ul squared minus ur squared, right? This is this equation here. In this case, f is u squared, so this is the equation that we get. And we can further develop this equation a bit and say, okay, this is 1/2 times ul minus ur times ul plus ur, right? So this is product of differences, and this is the difference of squares, right? So we have this formula here. And now we will focus on this part here. This part here is the time derivative of the integral of u over that domain, right? But as we saw, u is something that is constant, then there is a shock, and then it's constant again, right? So let us imagine that we have some shock, right, that is moving at a certain speed. We do not know, we do not even know if that speed is constant, right? But we have that discontinuity here, and that discontinuity will be moving with the solution, right? In this case, we have this equation, the discontinuity formed, and the discontinuity will be moving at a certain speed that we do not know yet what it is. But let's call that discontinuity S, right? That will be the speed of the shock. So this integral here will be, imagine that time is equal to 0, it will be a times ul plus a times ur, right? Do this. The first point will have a length of a, and the value is ul, and the second part will have a length of l, and the solution will be ur. But now the shock moved a bit. So now the limit of iteration will be from minus a to st, and from st to a. So the integration regions will be, if the propagation speed is positive, for example, this integration, this part will be a bit larger, and this part will be a bit smaller. And now we can take the time derivative, right? So ul and ur are some constant that we want, and when we take the time derivative here, the a values, right, disappear because they are constant. We do not derive with respect to time, and the shockwave propagation speed will be s, right, and this equation will transform into this, right? So propagation speed times the difference of u at the extremes, right? And this will be general. This does not depend on the f. This equation that we have here depends on the f, in particular, that we used, right? The fact that we used the Berger's equation gives us this equation here, but this part here, we did not use f at any point. So when we balance these two equations, we balance this equation here, this equation, we balance it with this equation here, we see that this term will cancel out with this term, right? And this is telling us that the speed of propagation of the shock in the Vargo's equation will essentially be the average of the solution at the two sides. If I did this for the general case, where instead of using the Vargo's equation u squared, I use some flux f, right? Then this will be the propagation speed. This is what's called the Rankine-Hugoniot condition, right? So here, when you did this, instead of having u squared, we will have some f of u, and the propagation 1/2 of u squared, we will have simply f of u, and the shock will propagate at this particular speed. Right? This is telling us how the shock is moving. So we do this, right? We see our solution here. This is what the ranking who will not condition is telling us. So we saw again that we have these characteristics at this side and these other characteristics at this side, and we have this solution here. And in this case in particular, we are considering that UL is greater than UR. Or in the more general case, it has to do with the f prime of u, the f prime of u at the. So this is telling me when UL is greater than UR, in this plot here in the characteristic line, is telling me that at the left the propagation speed is greater than on the right, right? So the solution is going this way, and they are mixing, right? They are colliding at some given point. Okay, so this is the initial solution. It has some discontinuity, and it will move at some shock speed that I give. And this speed of propagation cannot be any speed that I choose. It has to be a specific speed of propagation to satisfy the conservation equation. So the speed of propagation of the shock is given by the difference sides of the solution at the two sides, and it's given in such a way that the speed of propagation will the speed of propagation is given in such a way that the conservation law will hold, right? And this is much more powerful than it looks, because maybe you think, okay, but this is some weird problem where I have some discontinuity. Okay, but imagine that you did not have this, right? You did not have a constant solution and there is a discontinuity and a constant, but you have some solution that's smooth and then there is a discontinuity and then it continues the other way. Well, this condition will also hold, right? Essentially, what you do is you go very, very close until you take the limit until you get to this point here. So here you will take some limit of the solution until this u here, this integral here, will eventually boil down to this. So when you have some solution and there is a jump and then continue and you have that shock and you want to see what's the speed of the shock at a certain time, that will be given by this difference here, right? Have this continuity, you have the value of the left, the value of the right, you calculate the flux at both points, you divide by QL minus UR, and you get this. And I want you to really understand this here, right? So we have the solution. The solution here is propagating, for example, here is 0, and it propagates as it remains constant over time until the shock arrives, and then it starts moving this. The same one here. Notice how all the characteristic lines go to this particular point. What you can see is that this solution is a weak solution for a problem here. Okay? So if you put this in this equation here for any arbitrary fixed feed, this will work, right? Whatever fee choose. Not that hard to see when we actually replace the values here, right? And this is also the limit of the dissipative case. We add some dissipation and we take epsilon goes to 0. This is essentially what we will get. Key points here, right? The shock propagation speed is constant. I want you to also notice that all characteristic lines end in the shock. Right? There are no characteristic lines that are coming out of the shock. There is no information coming out of the shock. It's all going into the shock. So If anyone has any question up until this point, I think we can take a bit of a break, and then in the next part of the class, we will discuss what happens in the other case when suddenly we do not have this discontinuity like this, but we have it the other way around. So essentially what we have is that the straight lines are going up here. Here we have straight lines. And here we have these other lines, these slopes. And we will have a region here where there are no characteristics, right? There's no defined solution. And what we will see is that that has a very strong implication, which is that essentially we do not have a unique solution. We have infinitely many possible solutions, and we have to take some decision there to take the solution that makes the most physical sense when we solve. So I will pause right now. We will continue this at 10 20. Okay, give 15 breaks. So if you have any questions about what we are seeing right now, you can think about them and you can ask them later in the next part of the class. Okay. There you go. Okay. So in this case, these are the characteristics. This. Okay, so if you cannot see the board, okay, yeah, now it's better, perfect, right? So these are the characteristics that we are having, and we saw that they are kind of crossing, right? And this was the solution at the given time. Now here it is sharper, and eventually a shock forms. And we saw that if we just follow the characteristics, eventually we will have simply some multivariate solution of the problem, right? What we are saying here with the Rankine not condition is that actually what we will have is that this shock here will propagate at some speed, right? Once it forms, it will follow some curve. That maybe it's something like let's do it in white, reinitiated, something like this, right? Okay, this will be the characteristic of the shock. It's not necessarily a straight line. It can change the speed as the height of the shock changes. And now, from one side to the other, right? So we erase all these characteristics that are mixing, like this. They get together at a certain finite time, right? So for some time everything is nice, but then they continue and they go inside the shock, right? This way and this way. They all go into the shock and they get there. And what we are saying is that now this solution will be something like this, right? We are at a certain time, and then it will do a discontinuity, and then it will continue, right? This will be the solution that we are seeing, right? Now, recall that before, when we were following the characteristic lines, we were seeing something like this, right? Essentially, what we are having here with this condition of the shock speed guarantees that this is what's happening, that this area here and this area here cancel out. Okay, so we have this solution and we say, okay, we follow it, and at some point we put a discontinuity and we continue. And that discontinuity will be in such a point that these two areas cancel out perfectly. Okay, I want to check that all people are seeing. Okay, so this is the solution that we have. And what we must always have when we have this propagation, the shock, is that the solution that we have, right, the integral over the whole domain here, we calculate the integral, right, the integral from minus infinity to infinity, right, u x dx, right, this is a constant, right, this must hold always, right, which is the same to say that the time derivative of this is equal to 0, right? This is what we are saying. So this integral must be constant for evolution, and this is what will tell us how the shock is propagating, right? How this is. Maybe the shock gets smaller, maybe it gets bigger, depending on the problem that we have, and that will change the shock speed. But the full integral must be constant, for us to obey the conservation law. So I wanted to do that diagram to clarify a bit what's going on. Okay. So let's go back here to the notebook. Erase this. Right. So what we were seeing here is that in this solution here, where we have these characteristics that are mixing, suddenly I will have some curve here that goes right through the middle of these characteristics that are mixing, and this will give us a discontinuity that will be essentially the same solution that we have here, but with a discontinuity at a certain point that guarantees that the integral is constant when we evolve over time. So now we will try to see what happens in the second case. Or we were analyzing when UL was greater than UR. Or essentially we were thinking about the characteristics, so we are thinking about the derivative of f. In the Burger's equation case, this is essentially simply u, right? The derivative of f is u, right? Here, 0.5 times u squared, we derive by u, this is u. So this problem here, right, we were considering this case. Now we will consider the other case, when UL is smaller than UR. And we say, okay, we take this equation here, we have, right, where we calculated some shock speed, and let's assume that, okay, we had this discontinuous solution, and that discontinuous solution will continue to move, right? We imagine that solution will continue to move in time as some kind of shock, right? So in that case, we will get exactly the same propagation speed that we had before the shock. When we did this equation here, at no point did we use that UL or UR1 is greater than the other. So we essentially get the same propagation speed for shock. But now, this shock will have characteristics lines that are going outside of it. And I want you to notice this particular region here. So here, I want you to notice this characteristic here and this characteristic right here. So imagine you had the initial data, which is just this discontinuity that goes from 0 and suddenly is 1, right? I choose 0 to 1 just to make it easier to visualize, but it could have been any other values as long as they are different, right? And we see that in this part of the solution, all characteristics stay inside this region, so the solution propagates around here. And in this region, the solution always propagates on this side, right? It will continue. So here, I actually had no characteristics originally. I had no defined solution. So I have more freedom to do whatever I want there. I just have to put something inside here that fills and obeys the conservation law, and I will have some weak solution. In this particular case, I decided to put, okay, I will put some discontinuity that propagates at some speeds s, and this will be a solution to the system, right? And notice here that all characteristics are coming out of the shock. This will be very important later. So here, right? Here we have a different solution that we can propose, right? So here we are using this solution here, where now I am saying, okay, in this side, we continue this way, in this other side, we continue this other way, right? But right in the middle, right, the solution will not be neither UL but UR, but X over T, right? This function here. And this will give us all these characteristic lines that are going apart from each other. And what this translates to is that the discontinuity that we had suddenly disappears. It's still a discontinuity in the derivative, but it's not a discontinuity of the function. But the solution kind of goes sideways and it expands. This is essentially the same effect that we were having before, right? So if you notice, when we were solving, for example, let's say the Burroughs equation or the carriage equation, where we had these characteristics that were getting together, but here we also have some characteristics that are going further and further apart. So look at this profile here, it forms a shock, that discontinuity, but this part here essentially is smoothed out, it kind of spreads out, right? These are the cars that were going fast, and they had cars before that were going slower, so the distance between cars was larger and larger and larger as time went on. So this is what we are having here. But not only that, here I showed you two solutions. One is a shock that is propagating. The other one is what's called a rarefaction wave, right? So this is a rarefaction of the solution, and this will be true in general. But we can also construct any number of solutions. So I didn't plot it here, but here you have the equation, and you can put this here in the weak formulation of the problem, and you will have a solution of your differential of the weak formulation of the problem. So essentially here what I have is, okay, maybe I start with a rarefaction and suddenly I have a shock and I continue with the continuous function. So here I put some rarefaction and suddenly I say, no, starting from here, this is a shock, and the solution here, there is a rarefaction, here is a shock, and the solution here starts to go out from there, right? So it will be something maybe like this, right? Here I put some shock that's moving here. I say, okay, now from here on out the characteristics continue like this. And this will always also be a condition, a solution, right? Because essentially what we are satisfying here at all points is that the quantity is conserved. So if the quantity is conserved in any possible volume that we choose, then the solution will be a weak solution of our conservation law, right? So this runs into a bit of trouble because now we do not have a unique solution. We have infinitely many solutions. Maybe if the solution initially was smooth, okay, we can say, okay, yeah, we here we don't seem to have some issue with the rarefaction wave, but in this case, in the Riemann problem, we see it very explicitly. We had a region, we had no solution, and we can put infinite many things that satisfy the condition. So what will we do here? What we will do to solve this problem is again to think about the entropy condition, right? So we will take the problem with some dissipation. We will take the Burger's equation with some epsilon here and some dissipation term. And this, we know that has a unique solution. And then we will go back to the case where the dissipation goes to 0. And in that case, what we recover is essentially this solution. We will go to the dissipation goes to 0, right? This is what we will have, which is actually what makes most physical sense. And this is what we call the entropy condition. And I will try to give a very simple idea of what's going on in the entropy condition. But essentially, what the entropy condition tells us is that this kind of solution is forbidden in the physical sense. This cannot happen when I have a shock. All characteristic lines must go into the shock and they cannot go out of the shock. They must go all into the shock. So essentially, if I had information that's moving, right, at a certain speed, maybe I lose the information suddenly because I have discontinuity. The solution continues some other way. But what I cannot have is a region where I don't know what I should have, and I have some discontinuity, and from there I move it. Right? When I am moving this discontinuity here, I am creating information in some way that is coming out of the shock. What we should actually have is something like this, where you have this initial point here, and from there you spread out your solution. What we will see is that if we have some discontinuity that is propagating with some speed s, right, for it to satisfy the entropy condition, we must have this value here. So the derivative of f at ul has to be greater than the propagation speed, and the derivative of f at the right must be smaller than the propagation speed. Right? So what this is telling you is essentially, as I was telling you before, that the characteristics must end here. So this is the slope of the shock wave. The slope of the characteristics on the right must be larger, must be like this, right? Must be larger so that it runs into the characteristic, and on the other side it must be the other way around. We must get into the characteristic too, but the other way. They will all converge to that specific. What we can later prove some other moment if you want is see that these are actually weak solutions when we put them into the differential form of the. So up until this point, are you following me with these two problems that I show you? So about the shock formation and the rarefaction waves? Okay. So until now, we have been working, of course, only with scalar problems, right? And also in only one dimension, working only in one spatial dimension. We can always add more dimension in space, right? Because obviously, when we think about conservation laws, we are not always thinking about linear problems. We can think of a surface, of a volume, whatever it is. What this will give us is essentially several fluxes in several directions. So here, instead of having the derivative of x, I will have a term derived by x plus some flux derived by y plus some other flux derived by z, and so on, as many dimensions as I want. Because essentially what I have here in the original equation, right, this integral here, which is in only one dimension, will be in a specific box volume. Right? In any volume that I take, this integral here will be across the boundary, and this integral here will be inside some volume that I make, right? And this part here will transform in a divergence of some flux function. It will not be graded, it will be a divergence of some function f that we will here. And of course, I can also have some system of equation. cases where we were seeing were only with U, but we can always think of it as some system of equations, right? So, for example, what I want to here are the Euler equations that describe that describe how a fluid moves, right? At least in certain limits. So in the fluid equation, right, we will have three conserved quantities, which are the density of the gas or that we are trying to evolve, right? We will also have the momentum of the gas, which will be the density. The density of momentum will be the density multiplied by the propagation speed gas. So the velocity that the gas has at a certain point, and also the total energy of the system. So for example, this is the conservation of mass. This tells us that the density, the derivative of the density, will be the divergence of the momentum, right? Which, if you now think about in integral terms, right, and we integrate in space, this equation here, as simple as it is telling me, okay, I want to know how, if I take some volume here and I have some mass of gas inside that volume, how does the mass inside that volume change? Okay, it only depends on how much gas enters from the walls around that part and how much gas comes out of it. So this part here is the density times the velocity at the boundary. This is telling me, okay, the velocity is inside, going inside, there's gas that is going inside. If the velocity goes out, then the gas is coming out of the volume. And when we balance this all out, this will give us the total mass inside that volume and how it changes, right? So it's very, very strong. Of course, we could also think of this if U was some constant, right? This will essentially give us the advection equation. So if U is some vector that's saying, okay, the velocity is that way, okay, everything will go as advection that part. And then we also have the momentum conservation equations, right? Which will also have the pressure in there, right? And we will also have some energy conservation. So in this case, for U are conserved quantities, density, momentum density, the energy. The fluxes will be momentum, these other two quantities, times U squared plus the pressure. And the pressure, we need to provide some other way to close the system, because here we have a new variable here, the pressure, that we will use with, we can close with some equation of state. In this case, we will use the ideal gas state, the ideal gas equation, which will give us this equation of state that we can plug in here in the pressure, close the system completely. So now we are solving this equation here. We're saying, okay, the time derivative of U plus the gradient of f, and now we are thinking in one dimension to go back to the original problem. This equation here, we can write in this alternative way, where we have U, this is now a vector, times some matrix A times the spatial derivative of U, where this one here will be the Jacobian of f. The derivative of f with respect to the conserved quantities we have here. This is the same that we were having before in burgers, for example. This would be, instead of writing ut plus 1/2 of the derivative of u squared, I write, okay, ut plus u times ux, right? This u will be the Jacobian. In this case, it will be the Jacobian of this matrix, this vector that I have here. When I calculate the Jacobian, this matrix of this f, I will get this matrix here that I will not derive because it makes no sense to spend time doing that here. But if you take this equation here and you derive with respect to the conserved quantities, you will get this matrix. And this matrix will have some eigenvectors or some eigenvalues. The eigenvalues of that function will give us the propagation speed of the modes of the solution, which are the eigenvectors of A. So what this is telling us is that we can decompose this function u that we have here in some other variables, some other combination of linear combination of these variables. And this combination of variables will move constantly, right, along the characteristic lines that are the eigenvalues of this speed here. So in this case, we will have 3 propagation speeds. Right? We will be u minus c, u, and u plus c. We are at some point, we will have a mode that is moving with the fluid, and 2 other modes that are moving with the fluid but with plus c or minus c, where c is this quantity here, that is the speed of sound. So this tells us that when you have a fluid, right, some solution, initial solution, you will have 3 modes moving at 3 different speeds, with which have to do with the this propagation speed of sound that is moving information in that direction. Maybe we can think about, let me check if I here. Yeah, I wanted to mention, for example, was the lab. So let's recall the notebook that we had on the wave equation, right? To remember this. So our initial equation was this equation here. We added some variables and we transformed it into this equation from some quantities u and v, and then we have some other quantities here that are u plus and u minus, and we saw that this u plus and u minus will move like some advection equation. So this is essentially what is going on here. So think of it that this is the system that we have, and you try to think, okay, what are the characteristics of this system? Okay, you want to see the characteristics, you can actually linearize the problem, and you see the Jacobian of the flux that you have, right? Which is this one here. This is the flux in this equation, also a conservation law. And you see the Jacobian of the equation, and you will have 2 eigenvalues. One is going to the left, the other one is going to the right. And it will have 2 eigenvectors that will move across those characteristic lines, which are these 2 solutions, and this is what we were seeing here. When we do this with Euler, it will be exactly the same. We will have we can decompose this into some new variables. Instead of using u and v, use some linear combination of u and v. So here we will use some linear combination of the conserved quantities, and they will all move at their spatial velocity. Notice that the velocities depend on u, right? Depend on the speed of propagation of. So if the fluid has some different propagation speed at different parts, the characteristic lines will cross at some point. So we will have a shock. The wave equation, we did not have that issue. The characteristic lines never cross because they are constant. You never have that issue, but in this case, they will cross eventually, right? So we will have shock formations for the Euler equations, and we cannot even start with a discontinued data. In the wave equation, we can have a discontinued data, right? Of this equation here, we can think, okay, maybe my solution is discontinued at one point, and what will happen here is that the discontinuity will propagate at the speed of the advection. We will have no issue. And here we will in general have some propagation speed that we will need to fix. I wanted to show you some plots of this, but I make them in time. I will upload this notebook to Apuntes in a while, and then I will continue to refine it and add a bit more plots, make it clearer so you can see it. But oh, you right here. So for example, this will be the density profile, right, of the Euler equation after we do some evolution, right? So put some shock and we evolve over time, and we will have several discontinuities moving in different directions, and we can see all the things that we were doing before. So what we will see is that there are rarefaction waves that form, the solution spreads out, and there are also shocks that will move with the solution, and this is the general form of the Euler equation, right? So this is, for example, for the pressure, but we can do this for any other variables, and we also with the shock. And what we see here is what's going on. The solution here in the numerical solution that we'll try to tomorrow is that essentially we will add some dissipation, right? The problem to smoothen out this discontinuity. And the hope is that as the smaller the delta x we take, the sharper this is. And we can also make some high resolution methods which will be very, very sharp and will follow the solution almost perfectly. Of course, there will always be some dissipation. And if you do not add that dissipation, then you will have something like this. So if you take the finite difference scheme, you try to apply it, then you will have this strong oscillation. Tomorrow we will see some operators that try to solve this and do some good solutions that will essentially try to avoid these oscillations by using the conservation law. So here in this part, what I want to drive home is that our conservation law, when we are thinking in several dimensions, the spatial derivative that we have will transform into some divergence of some flux, right? Some flux vector. This will transform into some divergence, and the propagation speeds, the solution, will be given by the Jacobian of the flux. It take the flux, you take the Jacobian of that flux, and you calculate the eigenvalues, and that will give you the propagation speeds of the system. Yeah, that can give you information also on how shocks will form during the evolution. This various equation that did. Okay. So up until this point, are there any questions about what we saw today? Is there any part that you would like me to clarify, or is everything clear? I would like to know. There is any part here that that maybe was not clear. Maybe the characteristics were not clear, maybe the shock speed was not clear, maybe what to do with a system of equation was not clear, stuff like that. Or when we add more dimensions. Someone could write something. Any questions that have in the chat? I'm happy to repeat any part that we need to repeat. Okay. If there are no more questions, I will just do a quick overview and then we can stop for a while and we can focus on maybe doing some of the labs of some of the homeworks and trying to answer some of the questions, right? So we have some quantity u, right? And we know that the integral of the quantity must be conserved for domain, which means that it depends on some fluxes at the boundary of any domain that we want to iterate in. And we can transform this in some strong formulation, which has a derivative. If we try to solve this problem, we encounter that the problem will be constant along some characteristic lines, which in general will cross. So as long as u is some f of u is some convex function, the characteristic line will cross. So we will have multiple solutions at this point. So what we see is that a shock will form, a discontinuity will form that will propagate there, right? And what we saw is that propagation speed is specific to the problem, right? It must be so that the integral of the solution preserved, right? Discontinuity. That this solution will also be the limit of the dissipative case, where we take the equation and we add some small dissipation and we take the dissipation to 0, then we will get the solution. This solution that we are finding a solution of the weak formulation of the problem, so the integral way of seeing the problem thing, and also that we can have some rarefaction waves, right? From regions where initially the data is not the solution does not propagate into discontinuity. We have discontinuity in the initial condition, so in that region in space we do not have a solution. And what we are asking is that when we do that solution, right, if there is any shock in a region, all characteristics must go into the shock and not come out of it. And when we ask this, we have one unique solution that satisfies the entropy condition. All other solutions do not satisfy the entropy condition, are not the limit when epsilon goes to 0. So this is what we have to do. And if we want to take a system of equation, we can do so. We will have the characteristic speeds in terms of the flux that will now be a vector, and we can also add more dimensions to the problem, and the derivative will transform into some diverse. So in that case, I will stop the recording at this point, and we will continue a bit to revise some of the lab. So has anyone thought about any problems that they had with the labs or homework, so we can revisit? Or otherwise we can simply go as we go.